Swayam Prabha. Digital India. Educated India.
So, last class I have discussed how to get the response of your undamped force vibration under harmonic load and damped force vibration under harmonic load. Then I also discussed how we will get the response under periodic load by using the Fourier series, which is the summation of a series of harmonic loads, and I got the response for under periodic load also. Okay. So, now today I will discuss that how I will get the response of a step loading. So, sometimes loading there is no necessary that the loading will be only harmonic or the periodic. Loading can be in different form also. So, that means the next one, that is our case 6, which is the step loading. Okay. So, step loading means that we are applying a load. If I draw the time versus load plot, so this is QT. So, we are applying a load, then it is stopped. Okay. Then how we will get the response? So, this is your Q0 and this is applied up to a time of say TD, and then you will get the how we will get the response. So, now if I want to get the response, now for T less than equal to TD, that means within the loaded region, that means we have two parts. We have already discussed, that is your complementary solution, which is basically the transient response, and your particular solution, which is the steady state response. Now, in this case, when this is 0 to TD, what would be the transient response or the complementary solution? Or transient response. Okay. So, I can write this is complementary solution UT, that will be equal to, because if I go that solution, so this is the solution, that is my transient response, and this is my complementary response that I have discussed. So, this will be the transient response, this will be the solution response for that transient case, and this will be the steady state case. But now for the step loading, this will remain the same, this one. But what about the steady state case? Now for the transient case, this will be the solution, as I have already mentioned. This is omega 0 t, then C1 sin omega dt plus C2 cos omega dt. Okay. But for t less than equal to Td, for the steady state condition, because steady state condition, here you can see that this loading for steady state condition, it is only, this will be only Q0 by K, because it is not varying with time. Okay, because it is constant. Okay. So, it will be only if I say the steady state UST, so this will be only Q0 by K. Why? Because as loading is not changing with time and load is applied at t equal to 0 and instantaneously it is removed at t equal to td. So that means the loading is instantaneously applied at t equal to 0 and it is removed also instantaneously at t equal to td. Clear? So that means and the loading, as the loading is not changing with time also. So in such case I can write, because I have the equation m double dot plus c dot plus ku equal to q0. Now here this part will be 0 because it is not changing with time. So this part will be 0, or because as the loading is not changing with time. And then so I can write that my QS, if you write this is QS, 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 this will be simple Q0 by K. So that is the case Q0 by K. So final response for the loaded region I can write that is Q0 by K plus e to the power minus damping ratio omega 0 t into C1 sine omega dt plus C2 cos omega dt. Okay. Now C1 and C2 can be determined by using the initial condition, and initial condition that we know, that is your U0 at t equal to 0 and U dot 0 at t equal to 0. And if I put that, then I will get the solution or the response, that is K Q0 by K plus e to the power minus damping ratio U0 t. Now I will get the C1 and C2. So C1 will be U0 dot plus damping ratio U0 minus Q0 by K divided by UD into sum sine omega dt plus U0 minus K0 by Q0 by K into cos omega dt. Now from where I am getting this? Now here the within the loaded region the situation is damped force vibration. Okay, this is damped force vibration. So that's why I am getting this one. Damped force vibration is the two parts, one in particular solution and it is complementary solution or the transient response, because within the loaded region it is damped force vibration. And then I will get, if I put these values and this initial condition, I will get this solution. So you can try by putting this initial condition, then you will get the C1 and C2, then you will put there. Now for T greater than TD condition, what will be the thing? That will be free vibration, because here loading will not be zero, will not be applied. So what will be there? That in that free vibration you will get the equation and the initial condition for this region when T greater than TD, you will get the equation for response for free vibration. But if you need, when you need the initial condition, where you will get the initial condition? You will get the initial condition from this equation by putting T equal to TD. So you put T equal to TD, that your U and U dot, that will give you as an initial condition for the case if T equal to greater than TD. So for t equal to greater than Td, this condition, this is T and this is T equal to less than Td. So this here, this region, you will get the equation of free vibration, and then for the solution, for the response, when you need the initial condition, then you put the final condition of this, the loaded region. That means you put that from this equation, the damped force vibration, that equation that I have developed, from here you put T equal to Td, and that will be equal to the initial condition for T greater than Td case. Clear? So that I am not deriving, but you can derive that portion loading also beyond the loaded region. So, but I have derived the equation within the loaded region. Remember that. But you can derive the beyond the loaded region also. Now for the within the loaded region, now if I put that T greater than equal to Td case, that if my damping ratio is equal to 0, say, and u0 is equal to 0 and u dot 0 is equal to 0. If I put all 0, then I will get ut will be what? Ut will be q0 plus k, okay, and this is 0, okay, and this one is 0, this one is 0. So I will get that, what is the value? I will get that plus or this is minus. So what are the things are 0? So we have this one is 0 and qt is 0, and so this whole part is 0, and there will be only q0 by k into cos omega dt. Why this whole part is 0? Because this is 0, damping ratio is 0, so it will be 1. But this u dot 0 is 0 and damping ratio is 0, so this whole part will be 0. Similarly, this u dot u0 is also 0, so this part will be 0. Only this part will be there and minus this one will be there. Okay, so I can write this is equal to q0 by k 1 minus cos omega d t. So again you can write that what will be the u max, because in the response spectra it is the maximum response. What will be the max? So max will be, so this cos omega t maximum value can be minus 1. If it is minus 1, then it will be 2 q0 by k. That is the maximum value of u. Okay, so that can, because this cos can be plus 1 or minus 1, that is the maximum value it can give. If minus 1 plus 1, it will, the expression will be 0. If it is minus 1, cos omega dt is minus 1, then this will be q0 by k. Okay, and so this will be the response. Now I can write that q0 by k, that is equal to u static, you know. Okay, so my u max by u static, that will be equal to 2 here. Or you can say, if you write this maximum displacement, which is 2 times of static displacement. Okay, so this way I will get the maximum response of condition, and I have discussed all 6 conditions. From there you will get the maximum response. Now how I will get from here the response spectra, so that we'll discuss here. So now when I have discussed all 6 cases, the how to get the response, how to get the maximum value. So now I will get the, come back to the response spectra part. So response spectra part is for earthquake resistance design of structure. So where the entire time history may not be required. Okay, entire time histories may not be required. The earthquake resistance design is done based on the maximum value, absolute value of the response of the structure for a particular base motion. I have already discussed that how you will get the maximum value. Okay, so I will get the maximum value. I have discussed in a few cases that you can put that value can be last one. It was the 2 times of static displacement. Okay, so that is the maximum value or absolute value for the response of the structure to a particular base motion. Okay, now there may be acceleration response spectra, velocity response spectra, and displacement response spectra. Okay, so because as we know that there's these parameters that there will be acceleration, velocity, and displacement. So there can be acceleration response spectra, velocity response spectra, and displacement response spectra. The maximum values of acceleration, velocity, and displacement depends on only natural frequency and damping ratio. Okay, that depends on only natural frequency and damping ratio. So the maximum values of acceleration, velocity, displacement are referred as spectral acceleration, spectral velocity, and spectral displacement. So I have shown how you will get the maximum value for displacement. Okay, similar way you can get it for velocity and you can get it for acceleration also. A single degree of freedom system with infinite natural frequency or zero natural time period, its response spectra will be equal to peak ground acceleration. That means when your t is equal to 0 or frequency is infinite, because your frequency is 1 by t. If t is equal to 0, frequency will be infinite. In that case, your spectral acceleration, that will be equal to PGA or peak ground acceleration or PHA sometimes it is called. The expression of acceleration, velocity, and displacement time history can be obtained by using Duhamel integral for a linear single degree of freedom system. That means that we will get the expression for this acceleration, velocity, and displacement in time history that can be obtained by Duhamel integral. What is Duhamel integral? So let me discuss about the Duhamel integral, because that will be required to get the expression of acceleration, velocity, and displacement time histories. Okay, so now Duhamel integral, that I will just give an idea what is Duhamel integral. So that is okay. So for it can be used to get the response for any arbitrary loading condition when it is applied. So suppose this is your T and this is any arbitrary load, okay, and this is your QT, and we are taking a small segment on this loading function at a distance of tau, and thickness of this load is d tau. Okay, so here it is q tau. Okay, this is t. Now to do that, what I will do, I will take the help of some pulse loading. So we will get a Dirac pulse. So what is that? In that pulse loading, this is your say T and this is your QT, and I have applied pulse loading Q0 at T equal to T1. It is a pulse loading. So Q0 is applied over a duration of T1 that approaches 0, because this T is very small, it's a pulse loading, that means you apply it then remove it. Okay, so that means T1 is approaches to 0 and we are apply a load Q0. So that means using the Dirac delta function. So by using the Dirac delta function, what is Dirac delta function? That Dirac delta function is equal to 0 for your x not equal to 0 and equal to infinity for a particular x value, or not equal to, not equal to a actually. So that if it is only x equal to a, then there will be an infinite value. Otherwise, all the other places, if it is not equal to a, then it will be 0. So by using this, so that is a similar type of case here. Now here, when you apply this type of loading and then using the impulse momentum principle, we will get that Q0 into T1, that is equal to actually m into U0 dot T. Okay, and as T tends to 0, the T1 tends to 0, if it is T1 tends to 0, then I can write U0 T, that will be equal to Q0 T1 by m, and here that U0 is equal to 0. Okay. Now, if this is the case under this loading condition, then I will use this is as a damped free vibration. Okay, because this other region loading is not applied. It is only a portion where that is also tends to 0. So we will consider as a damped free vibration. Now, what is the damped free vibration? You know the response is what? Minus, I have already discussed for damped free vibration. This will be damping ratio omega 0 t, then U0 bar plus damping ratio omega 0 U0 divided by UD, then sine omega dt, then plus U0 cos omega dt. So let's go to the damped free vibration part. That is damped free vibration. So this is the expression I am talking about. So this is the expression that I am using. Okay, here this is the expression, that is the damped free vibration case. So now if I put these values, then this is the case, then I can write that this equation, that my U0 is equal to 0. So this part will not be there, this part will not be there. So only there will be e to the power minus damping ratio omega 0 t, and there will be U0 dot, this is not bar, this is dot actually. So this is not bar. So this will be dot. So this will be dot by omega d into sine omega dt. The other part will be 0 as U0 equal to 0. Now from here I can write finally that ut, that will be equal to e to the power minus damping ratio u0 t, and that u dot 0 is q0 t 1 by m into omega d into sine omega d t. Okay, so this is the equation. So this is the response for this Dirac pulse case. So now this Dirac pulse case is applied for a small duration. Now here we are assuming that this all section, this small section is equivalent to this one, and we will add this over the entire region of the loading. So now if that will do, so for arbitrary loading, so what I will do, I have applied the load at a distance of tau, the thickness is d tau, and I want to get what is the loading or what is the response at a time of t bar. So I have applied this load and I want to get the response at a time t bar. Okay, so I want to get that response. So now for what I will do for this particular condition using these expression, because I am considering this is one particular case which is similar to this pulse load, and then I will add them over the entire region. So now for this DUT, for this case DUT bar, because I want to get the response at t equal to t bar. So this is t bar, that is equal to e to the power minus damping ratio omega 0, that will be t bar minus tau, because it is from here at a distance of tau. So this will be t bar is the time where I want to get the response, and due to this load, which is thickness of d tau, and this load is q tau actually. So I will get this is the value, and then this will be the q0. So q0, that is q0 tau, that now we are applying, and then this will be t1 is how much? Here it was t1, now it is d tau. Here it is d tau, and then we have m omega d, then sine omega d, again this will be t bar minus tau, because this load is applied the distance of tau. So that means that your response you will get at t bar time, so that will be t bar minus tau. Now from here, if I, because the n number of pulse is being considered from t equal up to t equal to t bar, so that means the n number of pulse is considered up to t equal to t bar. So that means we have considered n number of pulse up to t equal to t bar, and we want to get the response at t equal to t bar. So I will get the from here ut or t bar actually, that will be equal to, so now we have to add that n number of response, we have to sum that n number of response, so that will be 1 minus m omega d, then summation of I equal to 1 to n number of pulse we have considered, so we have to add that n number of pulse, that will be e to the power minus damping ratio omega 0, then t bar minus tau I, because this distance now will change. Initially it was tau, that for one particular pulse. Now there is n number of pulse. So their tau distance will change. So that's why it is tau I. Okay. Then it is q, or this is q tau I. Then actually it is not q0. This is also, this should be q tau. Okay. So q tau 1, then sine omega d tau bar minus t bar tau I. So there is this d tau. So that will go up to t equal to t bar. Now as d tau tends to 0, because d tau is very small, here also t1 is very small, so d tau tends to 0. Now this summation will become integration. So now finally I will get the response at t equal to t bar, that will be 1 by m omega d 0 to t bar, then qt, then e to the power minus omega t u0 t omega 0 t bar minus tau, then sine omega d t bar minus tau d tau. So this is the integration form. So the analytical, it is very difficult to get the solution, but if I do the numerical integration, then we will get easily this solution. So that is the use of this Duhamel integral. So then we can convert this summation to integral, and then we can get the solution or the response under any arbitrary loading. So that Duhamel integration will be required to get the expression of acceleration, velocity and the displacement to get this response vector. Okay. So in the next class, I will discuss how finally I will get the response vector and what is the use of this response vector in the design. Thank you.